Okay, let's look at an example about Chinese remainder theorem. The question is, we're looking for a number which satisfies the following conditions. It's the smallest multiple of 10, which has remainder 2 when we divide it by 3, and remainder 3 when we divide it by 7. So once again, we are looking for a multiple of 10, but there might be many different answers, but we are looking for the smallest among them. But it also should satisfy the remainder 2. We should have remainder 2 when you divide that number by 3, and remainder 3 when you divide it by 7. Okay, first of all, the multiple of 10 means that number should be multiple of 2 and multiple of 5. Clearly, so if this number is multiple of 2, then when you divide that number by 2, the remainder must be 0. So we can say that number, let's say it's x, is congruent to 0 modulo 2. By the same reason, that number also must be congruent to 0 modulo 5. But it has two other conditions. The number should be congruent to 2 modulo 3 because of that condition, and the number is congruent to 3 modulo 7 because of this condition. So we are looking for that kind of number, and we need to check the condition for applying this Chinese remainder theorem. These four moduli must be pairwise relative prime, and 2, 3, 5, 7s are all prime numbers. Therefore, we can apply the Chinese remainder theorem, and we will find unique solution for that. Of course, it's 4 modulo to 10 comes from the product of these four moduli. Okay, then we need to find the capital Mi and Yi. Once again, this 210 is our capital M, right? So capital M1 is the number which is from that dividing that capital M by 2, the first modulus, then it's 105. By the same way, capital M2 came from dividing 210 by 3, the second modular, and 5, 7 we just put in a row. There's no specific orders of this, right? So we can just apply anything. Okay, so that's how we got 1, 2, 3, oh, it should be 4, it's a small typo, it's M4. Okay, that's the results. Then we already have that Yi is the inverse of capital Mi for modular Mi, small mi, right? So we are assuming that 2, 3, 5, 7 are small m1, small m2, m3, and m4. So for y1, we need to look at the inverse of 105 modulo 2, which means it's just only 1, right? 0 or 1, so 105 is congruent to 1, and 1 is inverse to itself, right? So it's congruent to 1. Okay, and for y2, we are looking for inverse of 70 for modulo 3, and 70 is congruent to, if you divide it by 3, 69, it remains 1 again, so it's congruent to 1 because 1 is inverse of itself. Next one, 42 is congruent to 2 for modulo 5. So if you multiply 3 to 2, it becomes 6, which is 1. Therefore, the inverse of 42 is same as inverse of 2 for modulo 5, once again, and it must be congruent to 3. So y3 must be 3. Okay, y4, we are looking for inverse of 30 for modulo 7. Then what is the remainder of 30 for modulo 7? 4, 7 is 28, so it remains 2, right? So what is the inverse of 2 for modulo 7? If you multiply 4 at 2, we got 8, which is congruent to 1 for modulo 7. So 4 must be the inverse of it. So this is how we found this capital MI and small yi's. Then, by the Chinese remainder theorem, our x must be sum of the product of these numbers in certain way. So the first, that is the congruency for first one. Sorry about the typos. It should be M1 and this M2, M3, M5, but this notation is just saying what real modulars for each of them, right? Okay, so the first one is for M1, Y1, and A1, small a1, for modulo 2, and in modulo 2, the A1 must be 0. So we're multiplying 0 with M1 and Y1. Okay, so it becomes 0. Whatever this number is multiplied by 0. So the result must be 0. And for this part is for modulo 3. Then A2 must be 2. So it's multiplied by 2 with M2 and Y2. Sorry about this. So 70 times 1. That's what it need here. So in the same way, 0 from this one, E3 for modulo 5 and M3, Y3. So, but it's just a 0 because it multiplies 0. The last one is for modulo 7. So A4 must be 3. So 3 times M4, Y4 is 30 and 4. So all together, this sum gives us 140 plus 360 is 500, but it's congruent to 80 for modulo 210. So our x must be congruent to 80 modulo 210. So we can say the smallest multiple of 10 satisfying this condition must be 80.